Hi there, my name's Andrew and I'm a PhD student at the University of Oxford studying climate physics. And today I'm going to be presenting some work I've done in collaboration with Paul O'Gorman at MIT. And in this work, we're really interested in trying to understand how and why precipitation extremes respond differently to climate change in different seasons. So to start off with, here I'm showing changes in seasonal precipitation extremes with warming across CMIP5 models under a future RCP 8.5 scenario. So here I'm measuring, and throughout the work, we measure extreme precipitation using the seasonal RX1 day metric. And what this measures is the maximum daily precipitation amount in a given season. So, it's like a 1 in 30 level event if you define it for a specific season. And what you can see straight away here, so you've got the changes in JJA extremes on the left and DJF extremes on the right, and the stippling indicates where the models are agreeing. And what you can see straight away is there are some similarities between these plots. So in both JJA and DJF, you see these decreases in precipitation with warming in the subtropical dry zones here. And you also see this amplification of precipitation extremes along the ITCZ regions. And because the ITCZ is shifted further north in JJA than in DJF, this band of intensification is also shifted further north. So you see these kind of consistencies throughout across both seasons. And in the southern hemisphere mid-latitudes in both seasons, you also see a fairly robust positive increase in precipitation extremes with warming, and the models are agreeing quite a lot on this. However, over the northern hemisphere mid-latitudes, and this really is what I want to draw your attention to, particularly in JJA, there's a lot of model disagreement, actually. So again, this plot on the left here, you can see that in the kind of mid-latitude band that I've highlighted, in JJA, there are quite weak responses of extreme precipitation to warming. And many places, for example, over the Mediterranean or over parts of the US, actually experience decreases in precipitation extremes with warming. And this is in stark contrast to what you see in DJF. So in DJF, across both land regions and ocean regions, you see this fairly strong, again, positive response of precipitation extremes to warming, and it's fairly robust across the models. Now, it's really important to understand why this happens, because as previous work has shown, over most mid-latitude land regions, the most intense precipitation event actually occurs in JJA. And so there's obviously a great societal significance for understanding why the models are predicting these changes and why they're disagreeing so much. So we really want to understand, why do they predict this kind of muted response to warming? Is it happening for a physically plausible reason? And can we see any hints of this happening already in the historical record? So first of all, to understand why the models are predicting this muted response of JJA extremes to warming over the Northern Hemisphere, we're going to use this simple physical scaling which was introduced by Paul and Tapio Schneider in their 2009 paper and used to great effect by Stefan Fahl recently, and he showed this works on regional scales as well. And this scaling basically assumes that what's important for precipitation extremes is two things. So firstly, the magnitude of the vertical motion associated with those precipitating events, and how much water vapor there is in the air to converge and form precipitation. And that's what's written here. So the angle brackets denote a mass-weighted vertical integral over the troposphere. You've got your vertical pressure velocity, this omega E, and then this term is the vertical derivative of saturated specific humidity along a moist adiabat. Now, this specific humidity term is just a function of temperature. And so what you can do, if you are considering changes in precipitation extremes with warming, is you can decompose this into a thermodynamic contribution, which is just resulting from changes in temperature on the day of the extreme event, and a dynamical contribution, which arises from changes in extreme vertical velocities, or vertical velocities on the day of the extreme event. So what I've plotted here on this top row is the contribution from changes in thermodynamics, these changes in temperature. And you can see that the thermodynamic contribution is spatially very robust across the models and also quite uniform. So in a given season, there's not much variation. And also you can see that between the seasons, the response is quite similar. Apart from the eagle-eyed of you might notice that in DJF, in this northern hemisphere region, there's like a strengthening of the response compared to JJA. But the real takeaway from this slide is that most of the interesting regional behavior is coming from the dynamical component. So within a given season, the spatial pattern of the changes in extremes is mostly set by this dynamical component. And the interseasonal variations are also set by the dynamical component. And it's in this context, again, that this summer-winter contrast becomes really apparent. So again, I've highlighted the same latitude bands here as I did on the previous plot, and you can see that in JJA, there's a really strong dynamical component over northern hemisphere land. It's actually quite robust across the models, you can see with the stippling. And in DJF, there's a weakly positive dynamic contribution to precipitation extremes, because there's a slight strengthening of updraft of these vertical velocities in these events. And this actually is quite nice because it explains why it starts to explain why you get this muted response to warming. So you're seeing that with warming, there's a cancellation between the thermodynamic component and the dynamic component over this region. And it also shows why there's a lot of model disagreement, because you're getting compensation between two competing forces, basically. So we can make this a little bit more quantitative by looking at zonal mean trends, so over land. So what I've plotted here in JJA, DJF, and the difference, respectively, I've plotted in blue the zonal mean trends in the thermodynamic component. In orange, the zonal mean change in the dynamical component, and then their sum, which is the full scaling, and which very well approximates what actually is happening in the models. And the bold lines here are the ensemble mean across the CMIP5 models, and then the shading indicates the 90% model range. So first of all, you can see if you look at this final panel on the right here, that this is showing the interseasonal contrast over land. You can see that the thermodynamic component doesn't change much between the seasons, except for when you get to the high northern latitudes, when it begins to contribute to this kind of contrast between the seasons. You get a strengthening in DJF compared to JJA. And you can also see, so when you look at on this panel on the right, you can see in the gray line this kind of dipole that appears around the tropics, and this is because, again, of these interseasonal migrations of the ITCZ. And so, in JJA, the ITCZ is moved slightly further poleward than in DJF, and you see the precipitation extremes track with that. And you can see that the reason that you're getting amplification along the ITCZ is mostly because of the dynamical component, so changes in vertical velocities. And then finally, over this latitude band that we have highlighted previously, you do see this really strong, significant dip in the seasonal contrast, where you get much weaker changes in JJA than DJF. And again, to first order, this is due to the dynamical component. So why is there this negative JJA dynamical component over northern hemisphere land? This is the real question we have to answer. And previous work has shown that we would expect, you would expect an increase in the moist static stability to lead to this weakened ascent and a negative dynamical component. So previous work, Ziwei Li's paper in 2020, Nye et al. And Tandon et al. Have also worked on this as well, and they've shown that this moist static stability parameter is really important for setting the response in the models that they've looked at. And so what we're plotting here, so in panel B, you've got the JJA dynamical component just as we plotted before, except for here it's only over land. And then in A, we've plotted the changes in the moist static stability parameter with warming, where we've calculated the moist static stability parameter on the days of the extreme event the days the extreme event occurs. And you can see, so physically we would expect like I said, we would expect an increase in static stability to weaken the vertical velocities and cause a negative dynamical component. And you can kind of see that you see this kind of negative anti-correlation happening in the spatial pattern. So wherever you have a strong positive increase in static stability, you get a decrease in this dynamical component, which physically makes sense. But it doesn't account for the intermodal spread. So if you take the average across northern hemisphere mid-latitude land for both of these quantities, and you plot it in a scatter plot, what you'd like to see is a nice straight line going from the origin all the way down to this bottom right here. But you don't see this, you don't really see any significant trend. And so while this moist static stability argument seems to capture some of the physics, you're not getting this these differences between them, capturing these differences between the models. So what we're plotting here instead is, so the panel B is the same as before, so this changes in the dynamical component, and in panel B we're plotting changes in near-surface relative humidity with warming in JJA. And you can see that that these changes in near-surface relative humidity actually match the spatial pattern of changes in the dynamical component really well. And if you take the average trend over northern hemisphere mid-latitude land for both these quantities again and do a scatter plot, you can see that these changes in relative humidity actually account for much of the intermodal scatter in the predictions. So why have we done this? Well, physically, we expect that there will be decreases in near-surface relative humidity over land with warming because of the land-ocean warming contrast, and also decreases in stomatal conductance. And what we're hypothesizing here is that over northern hemisphere land in JJA, precipitation extremes actually are fairly convective in nature. And most of the time they're coming from mesoscale convective systems and thunderstorms and things like this. So you would expect them to be influenced by these changes in relative humidity, because if you have a decrease in relative humidity, you will get an increase in convective inhibition. And what this is, so this is just a correlation analysis at the moment, but what this is suggesting is that there is this plausible mechanism whereby decreases in relative humidity over land cause an increase in convective inhibition, which inhibits these vertical velocities and causes a negative dynamical component. So we've shown that the CMIP5 models predict there are weaker changes in JJA than DJF over northern hemisphere land in precipitation extremes. But what we'd really like to know is, do we see any hints of this happening over the historical period? Because we're not necessarily sure that we trust the models over in northern hemisphere summer, because it is so convective. And so what we've plotted here is observed trends in precipitation extremes from the HADEX3 dataset from 1950 to 2017, and we've calculated the trends in we're taking 5-month seasons here, so it's May to September and November to March, just to increase the signal to noise a little bit. And here are the sensitivities to warming in 5-degree latitude bins, and you can see that there are increases with warming in both seasons across the mid-latitudes, but the increases are much weaker, again, in northern hemisphere summer than they are in northern hemisphere winter. And this results in a seasonal contrast which is consistent with what we see in the models. And indeed, I'm not showing this here, but it's in the preprint that this value that you get over the observational period is actually consistent with what you get when you look at the historical trends in the CMIP5 models as well. So in summary, we've shown that over northern hemisphere land, CMIP5 models predict that the fractional increase of precipitation extremes with warming is weaker in JJA than in DJF. And these changes, we've shown that they are primarily associated with a weakening of extreme ascent in JJA in these intense precipitating events. This dynamical contribution is highly correlated across the models with changes in near-surface relative humidity, both in terms of the spatial pattern and the intermodel spread. And this suggests that the mechanism could be through convective inhibition. So further modeling studies are needed to really confirm this, but it would be quite nice. It's a pleasing explanation, because it would allow us to link changes in summertime precipitation extremes to an aspect of climate change that we actually understand quite well, which is the land-ocean warming contrast and these decreases in relative humidity. And then finally, we've also shown that this summer-winter contrast is also evident in observations of precipitation extremes, and this is consistent with trends across the CMIP5 models in a similar period. So yeah, we have a manuscript in revision currently at GRL. Hopefully will be out sometime next year. And thanks for listening. If you have any other questions, feel free to reach out to me by email. So, thanks.